Welcome to the Solving Quadratic Word Problems, Day 1. So today we are going to be looking at solving quadratic equations, finding the roots, the x-intercepts, the zeros, but we're going to be applying it to some applications and so forth. So just like if we want to just kind of go over what we've been covering so far, you guys know that, okay, so, we've been looking at parabolas that open down. We've been looking at some that open up like that. And then, we've been like labeling things like the vertex, okay, like that. And then, if it was going through the x-axis like that, we would, be labeling things like the x-intercepts or zeros and so forth. Okay, so let's write that zeros. Okay, or roots. Okay, those are all the same idea. Okay, so what we're going to be doing is we're going to be analyzing a scenario where, I'll give you a quadratic equation, and sometimes I won't give you one, and then we'll be looking at and analyzing. Oh, okay, so what is the vertex? Okay, from this problem, but I might say instead of vertex, I'll say what's the maximum? Okay, and then oh yeah, that's related to the vertex, right? Or I might say, so if this is a soccer ball being kicked, when did it get kicked? So it would start here, it would get kicked, go in through the air, and then come back and drop. So I might ask you, when did it get kicked? When did it drop back to the ground? So in that case there, you're going to be finding things like zeros, roots, and x-intercepts, but I won't say go and find those. I'll say, tell me what time the ball landed. So you should be able to connect zero, roots, and x-intercepts to, finding, the times when the ball was kicked and when it landed. Okay. All right. And then, we can look at the scenario 2 here where you might be looking at, I don't know, a bridge and like the lowest point of the bridge, or, where's the bridge connected on each side. So again, you're looking at the zeros and x-intercepts, but I'm calling them bridge connections, or I might say, where's the bottom of the bridge? Then you should be able to translate that into, oh, that's the vertex and so forth. Okay. All right. So today, again, we are just going to be solving quadratic equations. But this week you'll be applying all of your knowledge so far. So like how to solve, like get things to factored form and solve. You know how to use the quadratic formula and solve. You know how to get quadratic standard forms to the vertex form by completing the square. So all of those different tools that you've learned will be used this week, okay? All right, so we'll start with the first one here. So today's examples, we will only be looking at, finding these zeros, the roots, the x-intercepts, okay? So you're not going to see instructions like go and solve the quadratic equations. You're going to see things like, here's a rocket, it's being launched, and it's, taking a path through the air, okay? So say this rocket here is going up, and then it's coming back down, okay, to the ground. So basically what we're analyzing here with this problem is, so we know that we have an equation here that represents the path of this rocket. So this here is the path of the rocket, and here's the equation that represents it. So it's saying that h is the height, so we put height here, so it's like h is like y, and then t is like x, right? So time goes here. So this is the time that passes, this is the height that the rocket gets to. So if we know the equation for the path of the rocket, the height is in meters and time is in seconds, I want you to tell me, when will Arlene's rocket here reach a height of 60 meters? Okay, so we don't know where the 60 meters is, but we're trying to figure out. Yeah, so if we know the height is 60 meters, what time is it? So I don't know, if we make a just kind of a guess here, say this was 60 meters here, right? So I want you to tell me, what time was that? Okay, right there. So if it was 60 meters in the air, what time was it at 60 meters? Okay, so so we're just going to go through and solve this problem. All right, so let's write down all the things that are given to us. Okay, so we know the height that we're analyzing is 60 meters. We have our equation. Okay, and our goal here the thing that's required is that we need to know the time. Okay, the rocket is at 60 meters. So we're going to go through, and because it's like asking you, find the time. Okay, so we need to find, think of it like the x values. We need to figure out the x values here, right? So it's t in this case. So since we have to do that, that means we have to get to the zeros. Okay, so we have to find the zeros. Okay, or again, roots or x-intercepts. That's what your goal is here. Okay, so what we've done in the past is that if we've had a quadratic equation and we needed to find the zeros, we would just go along and factor it. Okay, so factor it, or you can use the quadratic equation. Okay, so you need to factor or use the quadratic equation, or formula, sorry, quadratic formula. Okay, but like I said in the past, quadratic formula, it's a lot of work, a lot of writing and so forth. So if you can factor it first, I want you to try to do that first, okay? Okay, so we have our equation. Okay, and yes, we're going to try to factor it. But before we do that, we do have a piece of information here that's given. So we know that the height is 60, so we can actually plug that right in. Okay, because in the end, we aren't going to find, I guess, the x-intercepts. We're going to find the x values, but we're going to find the ones that, so say if the x-axis was here, we're going to find, the values that are here and here, okay? So we're going to plug the 60 in. All right, so now in order to factor and so forth, we need it to equal to 0. So I'm going to boot this 60 over. Okay, and then we get to there, okay? So that's equal to 0. So from there, now we can go through the steps and factors. So find the greatest common factor here. Okay, so you're noticing, okay, -5, get rid of that. And then any t's, no, okay, so just a 5. So divide that out. Okay, so write your common factor out here, and then clean this up here. Okay, so here 2 negatives made the 5s are gone, so that leaves a t squared that's positive. Okay, here positive 40 and -5 makes -8, and negative here makes positive 12. Okay. All right, and then from there, so now we're going to factor what's in here. Okay, so again, use guess and check method. Otherwise, if you are still comfortable with adding and subtracting, you have a simple trinomial here. Okay, so you have -8 to add to, but you have to multiply to 12. Okay, so hopefully when you go through and guess and check, or if you want to list them all off, you can do that as well. So you'll find that, 2 and 6 are good ones, okay? But so we need positive 12, but we need -8. So we need the negative values of both of these. That will add to -8 here, okay? So we'll keep going here. So now you can factor to here, okay? All right, so remember this 5, right? It could be divided away. So in the end, you're just looking at these 2 brackets here, and you're going to pop out the 2 values of x that work here. Okay, so we found that the times are 2 and 6. So what does that look like on our graph? So on here, we're finding, there's a 2, and then this one here is a 6, okay? So, and again, that's at 60. Normally, when we solved in the past, we would put h as 0. We would put a 0 here and then solve it. But in this case here, we wanted to look at 60. So it's almost like we move the x-axis up, and then we're looking at the 2 places where it'll be at 60. And that's 2 seconds and 6 seconds here. Okay, so it makes sense to have 2 because the rocket went up. It was 60 meters when it went up, then it went higher than 60 meters, and then when it came back down, it hit 60 meters again, and then went back down to the ground, okay? All right, so now you're the fourth statement. When will Arlene's rocket reach a height of 60 meters? Okay, so therefore, okay, the rocket Okay. We'll reach 60 meters at 2 seconds and at 6 seconds. Now that we've seen a rocket take off from the ground, go up into the air, and then land back on the ground, we're going to look at a scenario where the ball is being thrown off a cliff here, okay? So again, we have height involved here. Here's the equation for the height, and then we have time passing, okay? So we can label those onto this graph here. So here is time, here's the height, okay? So, so yeah, this equation here again models the path of the ball here. Okay, so see how it's negative? That makes sense because the parabola is going down, opening down. Okay, so our goal this time is how long will it take the ball to fall 20 meters below its initial height? So say this is the initial height here, where this yellow ball is here. Okay, so that's the initial height. And then from there, the ball is going to fall 20 meters below. So from here to here, 20 meters down, okay? So we need to, knowing that, we need to figure out how long it will take the ball to fall there. So basically, if we're looking at extrapolating here, so right there, so for the ball to go down, 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 down 20 meters, how long did that take? That's what we're trying to find here. So with the last example with the rocket, we knew, the rocket had to be at a height of 60 meters, and then we had to figure out the time at that point. In this case here, we know the initial height. We know that we're trying to analyze a height that's 20 meters down from the initial height. But in the end, though, we don't actually know what the height is here. So this height right here, we don't actually know what that height is. So we have to figure that out before we can kind of carry on with this problem. Okay, so we just know that there was an initial height and it dropped 20 meters. So we need to figure out h here in order to throw it into the problem so we can solve for what time values will work here, okay? All right, so from there, what we're going to do is we're going to figure out the initial height. So what's the initial height here? Okay, so you have actually studied this already before. Like if you have a standard form equation, you could actually find this just by looking at the formula here, okay? So, but if you can't remember, I'm going to just show you what to do, and then I'll point out what it is that we learned before, okay? So from looking at this, there is a way to just kind of look at the equation and figure out what is this point right here, okay? All right, so right now we don't know. So if you can't remember, this is what you do. So if you don't know, well, we know right here where it starts. What time is 0? Time is 0. What time is the initial time? It's 0. So if we know that t is equal to 0, I can plug it in here and then I could find the height. Okay, so if we plug this in here, so we get 0, and then we get 21 times 0, and then you add the 120, so that becomes 0, that becomes 0, so the height in the end is 120, okay, meters here. So that initial height here is 120. Okay, so right where the ball is released is 120 meters. Okay, and again, a really quick way of finding that is look at the constant value here of the quadratic equation. That's your y-intercept. That's what we learned, I don't know, back in cycle 2. So it's been a while, but so you should be able to find the y-intercept really quick by looking at a standard form equation. Okay, it's the value that's by itself here. Okay, so that's the initial value, the y-intercept, okay? All right, so now that we know the initial value, we can figure out, okay, so what height is it right here? So if we know that it fell 20 meters, so the actual height that we're going to use is 120 subtract 20 meters that it fell, and so we are looking at a height of 100 meters right here, okay, so 100 meters. All right, so at 100 meters now, what time did the ball, how far, when it dropped to 100 meters, what time was that, okay? So we need to figure this out here. All right, so this is our given. We know the height now, and we know the equation. Okay, so we need to find the time the ball gets to that height, okay? So again, because we are trying to find, these t values, we are, going to be factoring or using the quadratic formula, okay? So which I'll start writing as QF. Okay, so let's get our plan into action here. So we have our equation here. So again, we know that the h is 100, so we're going to plug the 100 in to the equation. And then we're going to go through and find the times that work for 100. Okay, so that starts with getting it solved, so that becomes 0. We're going to move this over. Okay, and then I don't know, you've probably already noticed that I draw my t's this way, where there's a little tail on it, so it doesn't look like the plus sign. So it's a kind of a good thing for you to do as well. Just if you're going to be, continuing with math and, science and so forth, so you're going to be using a lot of variables. Sometimes the variable's t, so you need to make sure your t doesn't look like your plus sign, okay? So I just put a little tail on the t. Okay, so keep going, clean it up. Okay, and then there we go. So now we have our equation, and so now we just have to solve for it. Okay, so here, again, you're going to try to factor. Do that first. Okay, so I'm looking here. A 21 doesn't have anything in common with the 20 or the 5, so the only thing that works here is a 1. But then, we don't want that first number to be negative, so let's get that negative out of there. Okay, so if I divide out a -1 out of all these, I'll get 5t squared, -21t, and then -20. Okay, all right, so then let's build our product sum table here, or you can do guess and check. Okay, so I'm looking at, it's a complex trinomial, so I have to add to -21, but I have to multiply to -100. Okay, so again, can't think of the values in your head, just go one by one. Okay, 1 and 100, no, that won't make 21. 2 and 50, okay, no. 4 and 25, nope. 5 and 20, nope. Okay, oh, sorry, hold on. 4 and 25, yes. Okay, so I could tweak, let's see here. I need to get a -100, and I need a -20, so I need to make the bigger number negative. Okay, so if I add these, I'll get to -21, but when I multiply them, I'll get to -100. Okay, all right, so we found our factors here, so we can use the decomposition method. So +4t and -25t. Okay, and then keep going. So here, I'm going to divide out a t out of both of these. And then this one here, I can divide out a -5. Okay. And so remember, this negative could just disappear. But anyway, I don't want to confuse you guys, so I'm just going to keep carrying it. All right, so in here we have t being factored out, so that's 5t plus 4. This -5 comes out, and that leaves me a 5t and plus 4 as well. Okay, and then keep going, almost there. Okay, so the first bracket, 5t plus 4, and the second one is t subtract 5. Okay, so now we have it nice and factored out. Okay, and then from there, we'll go on to the next page here. Okay, so again, don't worry about this part. This will disappear, but we're going to look at here to find the 0. So Again, remember when it looks complex like that, equal to 0. When it's like that, you know what, the opposite just pops out. Okay, so positive 5. Right here, we're going to kick the 4 over. Okay, and then kick the 5 over. Okay, and then get negative 4 over 5 and t equals 5 here. Okay, so now if we go back to our problem original graph here, so what I'm seeing here, so I'll draw it down here as well. So we know that we had you throwing the ball off, and then it landed, okay? And then, so basically I have a time that's 5 seconds. Okay, so it was in seconds, right? Yeah. So 5 seconds. But then I also have this time here. So if I change that to a decimal, that works out to be negative 0.8 of a second. So what is that? It's a negative. So if you were to extend this graph, sorry, over here like this isn't to scale, you would have negative 4 over 5 seconds right there, okay? But again, we threw the ball from here and started the time went down. So a negative time doesn't make sense. So in this case here, you'd say not a solution, right? It doesn't make sense to have negative time. So the only solution here that would work is this one here, okay, where its time is 5 seconds. So that makes sense, right? So sometimes when you get to a word problem answer, you need to kind of double check to make sure it doesn't make sense. Sometimes you can have a negative, but other times like time, you can't have negative time. So then you eliminate the one that you don't need. And then it's always good to write, show your teacher, okay, yeah, like I understand that I can't use that one because it doesn't make sense. So from now you can do a therefore statement. Okay, they wanted to know how long will it take the ball to fall 20 meters? Okay, so you can say, okay, it will take the ball 5 seconds, okay, to fall 20 meters down, okay, so from the initial height. All right, so yeah, so just that's what you need to do today. You're trying to find the, like it's kind of like the x-intercept. Sometimes you need to move the axis up, so because it might be at 100 meters instead of at 0 meters. And then you need to determine sometimes when an answer doesn't make sense here. So like with the rocket here, the times were 2 seconds and 6 seconds, and that was reasonable. You could have time that's positive, so that's on the way up it was 2 seconds, and then back on the way down 6 seconds. So that's why we included both times. But in this case here, we know we threw the ball and then it went down, so a time of negative 0.8 seconds, like the one that resulted from this side here, doesn't make sense. So we're not going to use that one. We just report the 5 seconds only. Okay, so now that we're moving on to the third example here now. So if you go through and analyze it, you'll notice that there's no equation. Okay, so we always had a quadratic equation that we could use in order to find the missing information here. So in this case here, we have someone diving. So they're diving off a 10-meter platform. So from from the ground all the way up 10 meters up, and then they're jumping. And this jump is in a quadratic shape. And so basically the maximum height that this person gets is 11.225 meters, and that's after 0.5 seconds. Your goal here is to figure out how long does it take for him to dive. Like how long does this whole dive take? So let's draw a diagram to kind of label everything that we know. So we have this person is jumping from a 10-meter platform here. Okay, so let's just, place it right there. Okay, so that's 10 meters. Okay, so that's the height, and we're looking at the time passing, so time here. So this person's going to jump and then dive into the water, okay, down here. So we know the platform that they jump off of is 10 meters here, okay? So from here, the maximum height that the diver gets is at 11.225 meters. Okay, and that takes from here to here, that takes 0.5 seconds. All right, so our goal here is to figure out um, if the diver reaches the maximum height of this after 0.5 seconds, how long was he above the water after he dove? So up and then down like that. So basically, we need to figure out the time, oops, that goes right here. Okay, so this whole dive process here, how long did it take? That's our goal, to find that there, okay? But we are given some information here, so we're gonna build a quadratic equation, and then we'll get to solving it. Okay, so here are all the things given to you. So you know the initial height is, 10 meters. Okay, so you know that the max height is at 11.225 meters, and that happens when it's 0.5 seconds since the start of the jump or dive, okay? All right, and then, yeah, that's all you know. You don't know any other information here. So your goal in the end is to find the time when, the diver goes into the water. Okay, so what's our plan here? So we need to build our equation, our quadratic equation, since we know it's a parabolic shape here. So we have some information here. We know what this point is here, which is the max, right? So we know the maximum height. So that is also, this max here is also what we've always been calling the vertex, okay? So we have the vertex, we have another point here. So we can build an equation here. We can build a quadratic, and because we have the vertex form, we can build the vertex form equation, which is this one here. Okay, all right, so if we can get to an equation, we should be able to go and eventually solve it, okay? So our plan is to get an equation first. So let's go through and fill this out here. So we know that the vertex is right there. So if we write this out, so we always write the x first, which is t. So we know it's 0.5 and 11.225, like that. Okay, so there's the point right there. We also know this point here, which is where the platform is, but it's also like the y-intercept. So in this case here, it's 0, 10, like that. Okay, so we know our 2 points here. So I want you to, like, if we're building a vertex form equation, this is the same as being the HK values of the vertex, and this is the same as being the XY values here. Okay, so from there we can fill everything in, and then we can solve for A. All right, so let's go through. So 10, Y is 10, A we don't know, X is 0, subtract H, which is 0.5, okay, bracket square, and then plus K is our max height here, okay? All right, so we found all the information here except A. Now we just have to solve for it, and we can build our equation. Okay, so we're gonna go through here. That becomes negative 0.5 squared. Okay, so just go through step by step, hacking it away and cleaning up everything. Okay, so that becomes A times 0.25. So remember, it's still multiplied here. Okay, and then equals 10. So again, if you want to rewrite this, because we always write the number in front, then the variable after, then you can do it like that. Okay, so now we just have to solve for A. So we're not going to move this first, we're going to move this one first because it's added on. Okay, so we'll do that. Oh, I'll subtract it over here. Okay, so we got that, and then we're going to boot this over, divide it away. So we'll do that over here. Okay, and because we already had decimals that we were working with, Okay, so some of the values were decimals. It's okay to actually, just keep working in decimals here. So that divided by the 0.25 ends up being negative 4.9. Okay, so our A value is 4.9. So now we can build our vertex form equation. So A is 4.9, negative 4.9, and then X subtract 0.5 and 11.225. Okay, all right, so we have our equation for this jump now, okay? So this dive. So we know the equation for this dive, the path of this dive. So our goal though is we still have to find that. We have to find the time it took from jumping all the way down into the water, how long that took. Okay, so in order to solve that, we have, so we know at this point here, we know what was the height at that point. So again, I apologize here. I used y and x here, but we should keep with the same letters. We have height, because they wanted us to use height for h and t for time, so I'll just change it. That matches the question. If it really bothers you, you can leave it as x and y, but there. Okay, so we need to find the time, but we know when we're right here, we know what is the height at that point right there. Well, the height is 0 because you've landed in the water. So we know the height is 0. Okay, so let's go through now. So this is kind of like part 2 of our solving. We're still solving. We're going to put 0 in for where the height is and write the rest of the equation here. Okay, all right, so all you have to do now is solve for t and you'll get your answer here. Okay, so we have lots of things happening here. We have brackets, we have, multiplied. So remember, when you're solving for a letter, we're going to use SUMDEV. Okay, anything that's added or subtracted will move first. So this is added. So we're going to boot that out of there, throw it on the other side. So then it'll be negative 11.225, and then the rest of the stuff that's left behind. Okay, so we took care of the adding, subtracting. Now we're going to deal with anything multiplied and divided. So that's this 4.9. So let's move that out of there. Okay, so we're going to divide that. Okay, and we'll get a positive 2.2908, and it keeps going. Okay, all right, so we're almost there. Keep solving. All right, so the next thing that goes on SUMDEV here is now we're going to take care of the exponent. So we're going to boot this exponent 2 over there. So when we do that, it'll square root over on the other side. And because you're an academic, you're in grade 10 now, you will write plus or minus, okay, whenever you square root. Okay, and so if we square root that, square root this value here, we'll end up with plus or minus 1.53544, etc. Okay, all right, so hopefully you see that there's actually 2 equations here that we can write now. So let's write them separately. Okay, so the first one will be where it's positive 1.53544 equals t minus 0.5. The other one is where it's negative 1.5135544 equals t minus 0.5, like that. Okay, so we're going to solve this one, we'll solve that one. Okay, so again, it's okay, this is normal to have 2 answers coming out of quadratics. Okay, so I'll boot this 0.5 over, so when I do that, it will add over there. Okay, and so when I add that, I will get, so t will make 2.0135 seconds, okay? All right, this one here, same thing, boot it over. Okay, so So you'll get the time of 2.01 and then time of negative 1.01. And again, if we're looking at analyzing what's happening here, so if we're looking at the dive, okay, so we had the person jump and then they dropped. So here, right at this point when they entered the water, that was 2.01 seconds. Okay, and then there would have been, like if we extended this out here, this is where the other x-intercept is. It's at negative 1.01 seconds, but again, that negative time doesn't make sense, so this is not, not a solution. Okay, so in this problem here, it doesn't make sense for time to be negative. But again, sometimes you'll run into problems where it's okay to have a negative, so don't just always eliminate the negative. All right, so after a lot of work, this is why this is in the final cycle. We're taking everything that you've been accumulating over the semester. You can now say, therefore, so the diver took 2.01 seconds, okay, because they wanted to know how long was he above the water after he drove, okay? So the diver was above the water for 2.01 seconds. Okay, so for this example here, it's an area length, perimeter type question that you'll see a lot today. So what you want to do, again, there is no equation, so you need to build that. So let's figure out what stuff we have here. Okay, so we have a rectangular field, and so it's enclosed by 100 meters of fence. So again, it's a rectangle and there's a fence going all the way around. Okay, so hopefully whenever you go around a rectangle like that, you understand that it means perimeter. Okay, so the perimeter is 100 meters. All right, so that's the fencing, okay? So from there, create a quadratic relation that shows the area of the field depends on its width. Okay, so we need, area and we need width, okay? So these are our variables. Okay, and because we have area meters here and the fence in meters, we'll have meters for the width and the area is meters squared. Okay, so so we need to create a quadratic relation and then determine the dimensions of the field that would result in the area of this. Okay, so we know in the end the area has to be this. We know the perimeter has to be 100 meters. Okay, so we need to know what the width and the length of the field will be. Okay, so say this is the length and that's the width of the field will be if we have the conditions that it has to have 100 meters and it has to have an area of 575 meters squared. Okay, so here's our plan. We need to build our quadratic relation here. Okay, so how do we go about doing that? Well, we have, area. Area is always length times width. Okay, so we know that equation for the area of a rectangle. So from there, what do we know about the width and the length? Okay, so, well, we know that the perimeter, so if we were to draw this again, so we know like the perimeter, which is adding up all the different sides here, equals 100 meters. Okay, so we know that if we go perimeter is, if we make the equation here, we know that it's 2 lengths plus 2 widths together will make 100 meters here. So we can make an expression here like that. Okay, so because we want a quadratic relation that shows the area with respect to the width, right? Okay, so if we're looking at this area formula here, we need area, we need width, but we don't want this length as well. So what we're going to do is we're going to solve perimeter here for length, and then we're going to plug it into here, okay? So again, if you're a little bit overwhelmed, like how was I supposed to know how to do that? You just, like once you see this one example, you'll know how to do all of these area perimeter type questions, okay? All right, so again, I'm going to solve for L here for length. Okay, because I want a quadratic relation that has A and W only in it. So move the 2w over, so that's 100 minus 2w equals 2l, okay, and then I'll move this 2 over, so that'll be 100 minus 2w all divided by 2 equals l, and then if we clean this up, 100 divided by 2 is 50, and 2 divided by 2, it just becomes w, like that. So there is our length formula that I can plug into our area formula here. So that becomes 50 subtract w times the w. Okay, so now I have a formula here that only has w's and a's in it, right? So for area and width. Okay, so now that we have our quadratic expression here, quadratic relation, we want to figure out what dimensions, what length and width will give us this area here, but also the perimeter of 100, okay? So I'm going to go through and I'm going to graph this for you so you can see visually what you're supposed to be finding. All right, so again, Google Desmos. Okay, start graphing, and then we will type that in. So A equals, yeah, so let's just pretend that's like Y equals bracket 50 minus X times X. Okay, sorry, that should have been a bracket, oops. Okay, so we have A equals bracket 50 minus W times W. So same idea here. So now we have our graph here. So we'll zoom out a bit here. Okay, so we're seeing, so what we have another, quadratic relation here. So what you're looking at here is you're looking at all the values of W. So this part's W and this is A area. So for, all of these values for width, these are the areas that you would get, okay? So if we zoom in here, we're looking at, for example, if you have 0 width, you have 0 area. If you have, let's see, a nice number here. So let's say if we have a width about, so if we're looking at, so it's like 5 here. So if we have a width of about 5, we have an area about 240, okay? So if you have a width of about, let's see here, 45, so if you have a width of about 45, you have an area that's around 240. Okay, so you have all these different area and width relationships. So if your width is about this wide, this is your area. If the width is about this wide, this is your area. So at some point though in this graph, you do have a maximum area, okay, or that you can have, or we want an area of 575, which is, whoops, right about here. Okay, so an area of 575 is right there. So we're trying to figure out what the width would be, okay? So see how it's it's not in a nice crosshair area. So we're gonna solve for that instead, okay? So here it is, here's the expression. So let's go through and solve for that. Here's our solve step. So we know our area from up here has to be 575. We've already used the 100 to build our equation. So here's the other condition. You have to have an area of 575 meters squared, equaling all this stuff here. Okay, all right, so what we're gonna do is, let's expand this out here. So it's like that W, like you could rewrite it this way. And you can multiply that W in. Okay, so multiply it here, multiply it there, so it becomes W squared. Okay, and then now let's get everything on the same side. So I'm going to move that over so you get a 0 left behind, and you'll get this minus 575. Okay, all right, so we have a quadratic here. It's not in the right order, so I'm going to put the W squared first. So it's negative W squared. Then I'll write this one next. That's positive 50W. And then I have 575 here. Okay, so again, let's go and graph this. So there was the general expression. So we had to figure out where it was at 575. So now if we graph this, so negative W squared, so I'm going to write X. So actually here, why don't I just write W? think it should be smart enough. Nope, it doesn't like that. Okay, so we'll go w squared plus 50x. Okay, subtract 575. So again, I just took the w's and changed it to x. All right, so there it is. We plotted it, so let's zoom in and out. All right, there it is. Okay, way down here. So if we're zooming in here, okay, so you could think of it as now these are the width values here, and so basically we're trying to figure out the zeros, the results, okay, for the w here that will equal to 0. So here are the two, right here and here. So we're going to find those right now by factoring or using quadratic formula. Okay, so again, so let's go through and look for a greatest common factor. So I'm noticing a -1 can be pulled out of all of these. So we'll divide that out. Okay, all right, and then let's factor these and we can get to the zeros. So, okay, so let's find the zeros here. So we're going to add to the middle term, which is -50. Okay, and we have a simple trinomial here, and we're going to multiply to 575. So those are the conditions. What are the two values that'll work? Okay, so when in doubt, just go through and just go one by one. So 1 times 575. Nope, that won't work. 2 doesn't work. 3 doesn't work. 4 doesn't work. 5 should work. So 5, 115. Okay, nope, that doesn't work. So kind of keep going until you find some results here. So I'm going through all the factors. It took me a while to analyze all the factors and to find that, hey, nothing works, okay? So, yeah, it just means that this isn't going to be a pretty answer. It's just going to be more of a radical answer and so forth. So let's go through and now kick in the quadratic formula. Okay. All right, so here is the quadratic formula. So again, in order to use this, you need to find your A, B, and C values and also take into account the negative signs that are with the values, okay? All right, so because we're solving for W, I made this W instead of X, okay? But again, if you're just more comfortable just leaving it as X, that's fine. So we're going to go through and again, you make sure you have the right formula and we're going to just plug everything in and we'll find our results here. Here and plugged, everything in for B, A, and C, put it in the right spots, and then I'm just going through now, cleaning up this one, negative makes positive, squaring that, there it is, multiplying this out, there it is, and we can just keep going here, get 200, and this is not a perfect square, so that's why it's good that we use the quadratic formula here. All right, so we're going to end up with two results here. We're going to have, the first one will be the one where we're adding to 200, the root of 200, and the other result is where we are subtracting 200 and then dividing by 2. Okay, so let's go through. And again, this is a word problem here. We do not need to actually go through and figure out the actual dimensions, so you can go right to decimals. Okay, but for fun, you can even practice keeping everything as a radical though before you're going to go to decimals. So to our side here, we need to reduce the root of 200. Okay, so you're thinking, all right, what goes into 200? What's the biggest thing that goes into 200? Okay, so we know 100 goes in, 100 times 2 makes 200. Okay, 100's a perfect square, so we can square root that. 2 we can't square root, so we'll leave it in the root. 100 will square root out to 10, so it becomes 10 root 2. All right, so we can plug that back into the expression here. So again, this is just a practice for next year. So we're plugging that back in. All right, and then I can simplify this out. So 50 divided by 2 is 25. 10 divided by 2 is 5 root 2. Okay, so there's the first one. And the same with the second one. You would end up with 25 subtract 5 root 2 like that. Okay, so now let's get them to decimals here. All right, so if I take 25 and add 5 root 2 to it, I'll get 32.07 and meters, and then this other one will be 25 subtract 5 root 2. Okay, and then this one will end up being 17.93 meters. Okay, so if we go back to the graph that we graphed in Desmos here, and just hover over those x-intercepts here, see, we'll find one was 17.9 and this was 32.07. Okay, so we ended up with the same values here as Desmos, but we did it through using algebra and the quadratic formula. Okay, so, but we're not done here yet. Our original question was determine the dimensions of the field that would result in an area of 575 meters squared, but also the perimeter of 100 meters here, okay? So in order to do that, we're going to go through and, we can plug it back into this formula here, okay, to find length, okay? So we know, so length is 50 minus W, okay? So since we know that the length is 50 minus W, so for the first one here, if I take this and subtract it from 50, okay, my length will be 17.93 meters. And then if I do the same thing here, I take my expression 50 minus W and I subtract the 17.93, I'm going to get the other one, 32.07. Okay, all right, so these are the two values that will work here. So it doesn't matter which one you label, the length or the width. I guess most people like to label the longer one the length and then the shorter one width, so either way is fine. All right, so therefore the dimensions, okay, so that means the lengths of the sides. The dimensions are 32.07 meters by 17.93 meters for the rectangle, for the field, okay? Okay, so again, that meets the conditions of it has to be an area of 575 and the perimeter has to be 100 meters. These are the two lengths and widths. Okay, so that's your lesson for today. So it's just basically what we did the other day when we were solving equations. We were trying to figure out, do we factor to solve it? Do we use a quadratic formula? Can we just simply solve a, vertex form equation in order to get to the answers? So we're trying to get to those answers today, and again with specific problems like shooting a rocket or throwing something off a cliff and so forth. Okay, so just there's two different types that you'll be studying today. One's where you will be given the equation, and then from there you just you plug in some information like, oh, the height's 60, so you plug it in and then you solve it. Okay, so solve it here by factoring. Here we had to do a little bit of work in order to find the initial height that we needed, which was 100 meters, but we had to kind of figure out where did you start. You drop 20, then you get to 100, plug the 100 in, and then again we used factoring here, but we had to use factoring by decomposition, and we got to the answers. All right, then we moved on to ones where we didn't have the equation at all, so we had to build one. So sometimes you have to kind of pull out all the tools. You know how to build vertex form, factored form, standard form. So yeah, just kind of look at what problems are information that you have and build the problem. So in this case here, we had the vertex, so we knew we had to use we could build the vertex form equation. So we did that here, we got it. And then from there, we had to solve it. So we had to find the time that it took for the dive. So we went through and just used SAMDEP and solved the equation. But again, remember that there's always these two results now because you're using quadratics. And again, so whenever you square root, make sure you write plus or minus, okay? So we ended up with two results here. One of them, again, didn't work. So then make sure to eliminate any answers that don't make sense. So negative time doesn't make sense. So just eliminate those. Sometimes you have to keep both, okay? Like we did up here with this one here. Okay, we didn't keep, sorry, the ones further later. Okay, so we had to keep both of them. So then we got to one where we were looking at, yeah, just a field. Okay, so again, this was a little bit more complex, but every time you see one of these now, you know what to do. You have to use both perimeter and area to get to solving the problem. So you start with perimeter and building a perimeter equation. From there, you have to eliminate one of the variables. So solve it for one of the letters. So in this case here, we needed to have width. So I solved for the other one, length. So I can plug it into my area formula here. And so then length is gone now. I just have width and area to deal with here. Okay, so that's what you're going to be doing every time with these rectangle area perimeter type questions. So once you get to there, this is actually a quadratic equation here. You're going to plug in the information you know, like, oh, the area is 575, so go through and solve it. And in this case here, it wasn't a straightforward quadratic, so after calculating all the factors out, you realize, oh, I should have used quadratic formula. So that's what we did. We went through, and it takes a lot of work in here. And then we got to these two results here. So these are two possible answers. But again, if you go find the length, it's the other value as well. So there's only one set of dimensions here that will get us to the area of 575 in the perimeter of 100 meters, okay? All right, so just please practice all the different ones of these today, because again, I've left these till the literally last cycles here, so that you're really good at factoring, you're good at building equations and so forth. So now you can tackle these tougher word problems.